In this lecture, we will introduce the concept of the GARCH PQ process, or the generalized autoregressive conditional heteroscedasticity order PQ process. To recap, the lecture you need prior to this one is the ARCH-Q process. So recall, if we have epsilon t being a white noise, mean 0, variance 1, AT is an ARCH-Q process if we have AT equals sigma t epsilon t, where sigma t is written here in expression 2, and the idea is sigma t is the conditional standard deviation of AT given Q past values of that process A, and we have some memory on the square of each of those past values with weight alpha 1 through alpha q. When we take that defining equation and square it, recall we get this expression, which is like an autoregressive process of order q in AT squared with multiplicative rather than additive noise. Such a process has zero autocorrelation for lags bigger than 0. Lags bigger than 0 in absolute value. We have conditional and unconditional mean 0, and a constant unconditional variance, which means AT is a weakly stationary process, which makes it a nice candidate for a noise term. But this memory in AT squared on the past causes conditional heteroscedasticity, or a non-constant conditional variance. And we saw that the AT squared process has the same autocorrelation as an autoregressive P, or if we're a little bit more careful, Q process in this case. Now, one issue that happens with ARCH-Q processes is we get high frequency oscillations in the conditional standard deviation or conditional variance. So that means high volatility is coming in short bursts. So looking at this, the issue here is that we're remembering the previous noise terms. And so those previous noise terms, especially if Q is small, you can have those situations where, suppose AT minus I is small, that means AT minus I squared is small, which contributes a small amount to sigma t, which means you expect a small deviation from the mean of 0 for AT. But having too few terms in here, or rather just the A's, can cause the periods of longer high conditional volatility or low conditional volatility to just be too short-lived. And so the idea is to give some more memory. And looking at this, we're saying the conditional standard deviation in an ARCH-Q can remember the previous noise terms, but we can also allow it to remember previous values of itself. And that's where we go from ARCH to GARCH, where we include the term generalized. So a GARCH PQ process, or a generalized autoregressive conditional heteroscedasticity PQ process, is written as follows, and this is the same definition as the ARCH-Q, but the difference is here we have memory on the previous conditional variance terms. So that's the only addition. And notice that if we say P equals 0, then you have an ARCH-Q process. So we are, in fact, generalizing from the ARCH-Q, because if you set P equals 0, you recover the ARCH-Q. Here we have the result of taking the defining equation for sigma t and squaring it. And now you see that in your sigma t, you have feedback from both the previous noise terms and the previous conditional variance terms. And so this dual effect, so think of it this way. Remember, think of AT being large. Or why don't we just pick a number? Suppose AT minus 1 is large. So suppose we have a Q is 1 and P is 1. If AT minus 1 is large, so is AT minus 1 squared. So this will contribute to a larger sigma t. But if AT minus 1 squared is large, that means we had a large deviation from the mean of 0 for AT minus 1, which should be reflected in a large sigma t minus 1 squared, a large conditional variance at that time. So this will also contribute to sigma t being large. So that large a sub t minus 1 contributed to both of these terms being large, which contributes to sigma t being large. And so that allows you to have more persistent periods of high conditional volatility because you're getting the contribution both from the square of the noise term itself and the previous conditional variance term. You can make the same argument for low. If AT minus 1 is small, so is AT minus 1 squared. This term would contribute a small amount to sigma t. But since AT minus 1 was small, you had a small deviation from AT's mean of 0, which means we should see a small conditional variance at time t minus 1. And so this term would contribute a small amount to sigma t. The result would be a small sigma t, and so we should expect a small deviation from the average of 0 for AT. As in the GARCH process case, AT is weakly stationary, so we have mean 0, we also have conditional mean 0, and we have a fixed variance. It has no autocorrelation, and so remember what we're really seeking for here is that this makes it so AT is a good candidate for a noise process. Remember, for a noise, think of the defining properties of white noise. Weakly stationary, no autocorrelation, mean 0. We have these key properties, but the difference is that there's no autocorrelation, but there is some auto-dependence, and that is showing up in the second conditional moment. Well, really, in the second moment, we have the autocorrelation of AT square matches that of an ARMA PQ. And again, that's because this looks like an ARMA PQ with multiplicative rather than additive noise. So you have, it may be easier to think of it with equation 8. Sigma t is remembering previous values of itself and previous values of the noise terms. So this looks like something ARMA, and in fact it has the same autocorrelation structure. And so this gives us a robust noise term with many different forms of autocorrelation to model AT square. And this is t square here. So when you think about an example like financial modeling, oftentimes it is in fact the variance that looks like it's not constant. Now, we can still use these financial models with time series that have constant variance, namely stationary time series. But the conditional heteroscedasticity in this GARCH model allows us to model what look like time-changing variance properties in time series data via this conditional standard deviation or conditional variance. And so we're using this feedback from the previous values in the data to update our guess at the variance, right? You can think of conditional variance as your guess at the variance, seeing the recent information. And if you think about syncing this with data, this becomes fairly nimble compared to what you would do for an estimate of unconditional variance. So for example, suppose you have data. You have the following time series data. So you have, say, y1 up to yn. Well, how do you estimate your unconditional variance? You take the sample variance, right, which we know is the average using n minus 1 of the square of the deviation from the sample mean, right? But suppose we're doing a GARCH 1-1 process. In that case, we have our formula for our conditional variance, which we get from 8 here. So we would have sigma t squared is equal to alpha naught. Right, so we get alpha naught, and then we'll have one term for the previous noise term itself, the previous GARCH term, and one term for the previous conditional standard deviation term. Right here, so squaring both sides of 8 is what we're doing. So we get plus alpha 1 times at minus 1 squared plus beta 1 times sigma t minus 1 squared. And so this is our conditional variance. And notice these two things are looking back very differently in time in the data. So if we look at our timeline, so say we're indexing time, we have time 1, 2, 3, we have n minus 2, n minus 1, and n. And if you think of a look-back period for each of these, so suppose we have our look-back period for the sample variance highlighted in this orange. Well, that's looking back the whole way. If we highlight in green the look-back period for the conditional variance, in this GARCH 1-1 example, we're only looking back one time step. The point is, relatively, for the sample variance, we are looking much further back in time with n data points, whereas the conditional variance, we're looking, in this case, one step back. But even if you had a GARCH 2-2 or a GARCH 3-3 or a GARCH 10-10, typically n is going to be much bigger than something like 10 when you're doing financial modeling. And so you're looking back far shallower in time to update your conditional variance than you are for the sample variance. So think about now doing this with a rolling window. So right now you're standing at time t, but then if we advance the clock to time t plus 1, when you're doing things on a rolling window, all of this shifts forward. So you'll have these same data points. You add your new data point at time n plus 1 and throw out the oldest. That's typically what we're doing when we're doing a rolling window. You're looking at, or a trailing window, you're looking at the most recent n data points to update everything in your model. Well, suppose after time n, when you hit time n plus 1, something really changes in the market. Or maybe we could say even more, a better illustration would be, at time n something happens. And so this new data point maybe something very tumultuous, something causes very tumultuous market conditions. So a data point that you add at time n is competing with all of these other data points for the sample variance. But it's just one of a few for the conditional variance. So when we move forward, our sample variance calculation to estimate the unconditional variance has thrown out the oldest data point and added the newest data point. But that new data point is just one of n data points. That doesn't change this expression all that much because think of n as very, very large. But in the case of our conditional variance, we see that this window, at least in this GARCH 1.1 case, shifts forward and is only looking at the most recent 2 data points. That change from yesterday, from time n, will be immediately reflected in the conditional variance. It will take a while to be reflected in the sample variance. We will need more and more data points into the future, and so our estimate of the unconditional variance is going to be lagging and kind of sluggish to catch up with a quick change in market conditions, whereas the conditional variance with this GARCH model picks it up right away. So we can think of it as a nimble way to pick up on changes in market volatility in this type of model, because we get to model the conditional variance and have this expression that is looking back far shallower in time than when we model things unconditionally. And in a future lecture, we will explore how you use this GARCH process as a noise term. In particular, we'll look at the GARCH 1.1. So I encourage you to watch that lecture as well.